Welcome all, I am Maria Vincent, Assistant Professor, Department of Electronics and Communication Engineering, Rajagiri School of Engineering and Technology. Today I will be discussing on the topic double sideband, suppressed carrier, single sideband and vestigial sideband, which comes under the course Electronics Communication for S7 EE students. In this slide we are going to detail the concept double sideband suppressed carrier modulation. So in the previous lecture we already found the disadvantage of conventional AM, where it can give a maximum efficiency of 33.33%, and we introduced this double sideband suppressed carrier, where the carrier signal is suppressed in this modulation technique. So when the carrier is suppressed, the total power is equal to the sideband power, so 100% efficiency can be achieved. So if you are suppressing your carrier signal, then that modulation is known as the double sideband suppressed carrier modulation. So the practical significance of double sideband modulation is the reduction in transmission power required to cover the same area. So in this case we can suppress the carrier so that the power, the transmission power can be reduced. In case of conventional power, a lot of power is got for transmitting the carrier. So if we are suppressing the carrier signal, that power, the transmitted power can be reduced. So the reduction in the transmission power reduces the amount required for the equipments. So these are the advantage of double sideband suppressed carrier. In this slide we are going to derive the expression for a double sideband. So in the previous lecture we already derived the expression for conventional AM signal, which is given by E of t is equal to 1 plus m into cos 2 pi fm into t into EC cos 2 pi fct. So this EC cos 2 pi fct represents your carrier signal, which is used to carry your information with amplitude EC and frequency FC, and this m represents the modulation index, which is a term which is used to describe the amplitude change within the AM waveform, and this cos 2 pi fm into t represents your modulating signal with frequency FM. And this 1 plus m into cos 2 pi fm into t contains a constant plus modulating signal component. So this 1 represents the constant value, and this m into cos 2 pi fm into t represents your modulating signal component. So in case of double sideband, if you try to remove this constant value, then your equation, your modulated wave is become m into cos 2 pi fm into t into EC cos 2 pi fct. So in this equation, this 1 represents what? The constant value. If you try to remove this constant value, then the AM modulated wave is become m into cos 2 pi fm into t into EC cos 2 pi fct. So for an ease of analysis, we have to make use of one trigonometric formula, that is cos A into cos B. So cos A into cos B is equal to cos A plus B by 2 plus cos A minus B by 2. So the same relation can be used here. So the equation can be rewrite as m into, so the amplitude is m into EC by 2 into cos 2 pi FC plus FM into t plus m into EC by 2 into cos 2 pi FC minus FM into t. So this is the expression for the double sideband signal. So this a modulated wave contain only the upper sideband as well as the lower sideband. So in this modulated wave we suppressed the carrier. We are only transmitting these two sidebands in order to get a maximum efficiency. So this is what double sideband signal. So in the previous lecture we already discussed the double sideband full carrier. In that case that modulated wave contain three different signal components, that is a full carrier component, then upper sideband and lower sideband. And in this case double sideband we are transmitting only the two sidebands, that is upper sideband and the lower sideband. So here we are suppressing the carrier signal in order to achieve the efficiency as 100. So if you know the expression for the double sideband signal, then we can draw the frequency spectrum. So in this double sideband we are having two sidebands, that is upper sideband and the lower sideband. So in the frequency spectrum on the x-axis we are having frequency in hertz, and the upper sideband is having the frequency at Fc plus Fm with an amplitude of m into Ec by 2. So in the frequency spectrum at Fc plus Fm we are having a upper sideband of amplitude m into Ec by 2. Similarly at frequency Fc minus Fm we are having amplitude of m into Ec by 2. So from the expression we can draw the frequency spectrum. So when compared with the double sideband full carrier, in this AM modulated wave we are having only the upper sideband and the lower sideband. So the carrier signal component is suppressed in order to achieve the maximum efficiency. So if you know the frequency spectrum, then we can easily find out the bandwidth. So the bandwidth is equal to higher frequency minus the lower frequency. So in this spectrum it is understood that the higher frequency is Fc plus Fm and the lower one is Fc minus Fm. So the bandwidth is equal to Fc plus Fm minus of Fc minus Fm. So this Fc got cancelled and the bandwidth is equal to 2 times Fm. So which is same as that of double sideband full carrier. So both the double sideband full carrier and the double sideband is having the same bandwidth as 2 times Fm, but the only difference is we can reduce the transmitted power in case of double sideband because we are suppressing the carrier signal component. So this is what double sideband ring modulator. In this slide we are going to discuss about the double sideband generation with the help of a balanced ring modulator. So the modulating circuit that inherently removes the carrier during the modulation process is called as the double sideband suppressed carrier modulators. And the circuit that produces a double sideband suppressed signal is called as the balanced modulator or the product modulator. A balanced modulator has two input signals, a single high frequency carrier signal and the modulating signal, which may be a single frequency or a complex waveform. And this balanced ring modulator is constructed using the 4 different diodes, that is D1, D2, D3 and D4, and 2 different transformers, that is T1 and T2. So T1 at the input side and T2 is at the output side. So for balanced modulator to work properly, the amplitude of the carriers should be very much greater than the amplitude of the modulating signal. So this carrier amplitude should be very much greater than the amplitude of this modulating signal in order to work properly. Now we'll discuss the operation of balanced ring modulator. So the diodes D1 to D4 are electronic switches that control whether the modulating signal is passed from input transformer T1 to output transformer T2 as it is or with 180-degree phase shift. So the diode D1 to D4 are connected in a ring manner. That is why the circuit is known as the balanced ring modulator. So to understand the working principle of this balanced ring modulator, we have to consider the two different cases. So the case 1, the D1 D2 biased on. With the carrier polarity as shown in the figure, here it is a positive polarity and the negative polarity. So in the secondary windings, here it becomes plus and here it is minus. So because of the carrier polarity, the diodes D1 and D2 are forward biased, and it will act as a closed switch, while the diodes switches the D3 and D4 are reversed biased and act like a open switch. So consequently, the modulating signal is transferred across the switches to T2 without a phase reversal. So directly your modulating signal is transferred from T1 to T2 without any phase reversal, because we are having the same polarity as plus minus. So the modulating signal is transferred from T1 to T2 without a phase reversal because the polarity is same. In this slide, we'll consider the case 2, that is D3 D4 biased on. So when the polarity of the carrier reverses, that is minus plus, the diode switches D3 and D4 will be in forward biased, and it is act like a closed switch, and similarly the diodes D2 and D1 are in the reverse biased, which is act like a open switch. So consequently, the modulating signal undergoes a 180-degree phase reversal before reaching the transformer T2. So it is clear that at T1 the modulating signal is having a polarity plus minus, but because of this D3 and D4 at T2 there will be a 180-degree phase reversal, that is represented as this minus and this plus. So there will be a 180-degree phase reversal. So then we want to know how this carrier signal is suppressed in this circuit. So the carrier current that flows from the source to the center tap of the transformer T1 and T2. So at both the input and at the output, we are using the two different center tap transformer where we are giving the carrier signal. So at the center, your carrier signal it got split up, and the current flows in the opposite direction through the upper and in the lower half of the transformer. So because of that, a magnetic field is induced in both the upper and the lower half of the transformer with equal magnitude. So it got cancelled. This is how the carrier is suppressed in the balanced ring modulator. So in the balanced ring modulator, it will suppress your carrier signal only with the help of this center tap transformer T1 and T2. So the carrier current flows from the source to the center tap of T1 and T2, where the carrier signal is got splitted, and because of that there will be a current and it will flows in the opposite direction through the upper and lower half of the transformer. So because of that current, a magnetic field will induced, and that in both the upper and lower half of the transformer, but both are in the same magnitude but opposite in polarity. So this is how the carrier signal is suppressed in the balanced ring modulator. So if diodes are not perfectly matched, or if the transformer are not exactly center tapped, the circuit is out of balance and carrier is not totally suppressed. The output from balanced modulator consists of series of RF pulses with repetition rate determined by RF carrier swinging frequency, and amplitude is controlled by modulating signal. The output waveform takes the shape of modulating signal, except that alternating positive and negative that correspond to polarity of carrier signal. It is called as doubly balanced modulator because the circuit is balanced to reject both the modulating signal and carrier signal using a ring of diodes. So in the balanced ring modulator, we are using the 4 different diodes which is connected in a ring fashion. So that is why it is called as a doubly balanced modulator, because the circuit is balanced enough to reject both the modulating signal and the carrier signal using a ring of diodes. So the waveform shows the input and output waveform associated with a balanced modulator for a single frequency modulating signal. So here the A signal represents the modulating signal and the B signal represents the carrier signal. It can be seen that the diode D1 and D2 is conducting only during the positive half cycle of the carrier signal, and the diode D3 and D4 is conduct only during the negative half cycle of the carrier signal. So the output from the balanced modulator, which is represented in D, is consist of a series of RF pulses whose repetition rate is determined by the RF carrier switching frequency, and the amplitude is controlled by the level of this modulating signal. So if you observe, it is clear that that repetition rate is controlled by the carrier signal, and the shape is determined by the shape of this modulating signal. So consequently, the output waveform takes the shape of the modulating signal, except with alternating positive and negative polarities that corresponds to the polarity of the carrier signal. Now we'll discuss the single sideband AM. So you may notice that as we change from AM to double sideband, there is no improvement in bandwidth. In both double sideband full carrier and double sideband suppressed carrier, the bandwidth is same as that of 2 times FM. So only the efficiency was improved. So from 33.33% we improved to 100% in case of double sideband. So in communication, we need to multiplex more number of signals. So for that, the bandwidth should be minimum. In communication, we have to maintain the signal bandwidth as small as possible than the channel bandwidth. Then only we are able to accommodate more number of signals over a single channel. So hence we go for single sideband modulation, in which only one of the sideband is transmitted. So in conventional AM or in double sideband full carrier, AM modulated wave contains 3 different signal components, that is a carrier component, then upper sideband and the lower sideband. And in case of double sideband, that AM modulated wave contains only the 2 different sidebands, that is upper sideband and the lower sideband. So in case of single sideband, we are going to transmit only one sideband, that is either will transmit lower sideband or the upper sideband. So now we'll detail the time domain equation. So the expression for the single sideband is given by S of t is equal to Ec into Em by 2 into cos 2 pi Fc plus or minus Fm into t. So this plus represents the upper sideband signal and this minus represents the low sideband signal. So if it is Ec Em by 2 into cos 2 pi Fc plus Fm into t, then it is upper sideband signal. If it is Ec into Em by 2 into cos 2 pi Fc minus Fm into t represents the lower sideband signal. So by using the trigonometric identity, that is cos A plus B or cos A minus B, we can rewrite this equation as Ec into Em by 2 into cos 2 pi Fct into cos 2 pi Fm into t minus plus Ec into Em by 2 into sin 2 pi Fct into sin 2 pi Fm into t. So this is the final expression for the single sideband signal. So either will transmit a lower sideband or upper in order to improve the bandwidth, means in order to reduce the bandwidth. So the total transmitted power become Pt is equal to either the upper sideband power or the lower sideband power. So if you are transmitting the upper sideband, then Pt is equal to PUSB. Suppose if we are transmitting the lower sideband, then the total transmitted power is equal to the lower sideband power. So the Pt is equal to Vrms square divided by R, which is equal to Ec into Em by 2 into root 2 the whole square divided by R, where R is the load resistance. So which is equal to Ec square into Em square divided by 8R. So compared to the double sideband, both the bandwidth and power reduces to 50% in case of single sideband. So now we'll discuss the power saving in case of single sideband. So the equation for the percentage of power saving is equal to power saved divided by the total power into 100. So when a AM, conventional AM is replaced with double sideband, the percentage of power saving is equal to the total transmitted power for the conventional AM minus the power for the double sideband power divided by the power used for the conventional AM into 100. So the power for the conventional, the total transmitted power for the conventional power, which is already derived in the lecture 2, which is Pt is equal to Pc into 1 plus m square by 2, and for the double sideband it is m square into Pc by 2. So it is the percentage of power saving is equal to Pc into 1 plus m square by 2 minus m square into Pc divided by 2 the whole divided by Pc into 1 plus m square by 2, where Pc represents the carrier power and m represents the modulation index, which is a term which is used to describe the amplitude change in the AM signal. So which gives the power saving. So the percentage of power saving when AM is replaced with double sideband, which is equal to 2 divided by 2 plus m square into 100. So when the AM is replaced with single sideband, the percentage of power saving is equal to power for the total transmitted power in conventional AM minus the total transmitted power in the single sideband divided by the total transmitted power which is used in the conventional AM into 100. So which is equal to Pc into 1 plus m square by 2 minus m square into Pc by 4 whole divided by Pc into 1 plus m square by 2 into 100. So the percentage of power saving is equal to 1 plus m square by 4 the whole divided by 1 plus m square by 2 into 100. So this much power can be saved if you replaced from AM with single sideband. In this slide we are going to discuss about SSB generation with the help of a balanced modulator filter method. So the early SSB transmitter used the balanced modulator circuit to generate the double sideband suppressed carrier signal, which is followed by a sideband pass filter in order to remove the unwanted sidebands. Such a transmitter is illustrated in this slide. So the initial modulation is take place in the balanced modulator at a low frequency because of the difficulty to make this filter at a high frequency. So the filter is a band pass filter with a sharp cutoff at each side of the band pass to obtain the adjacent sideband rejection. So the filtered signal is up converted in a mixer to the final transmitter frequency and then amplified before being coupled to the antenna. So the linear power amplifiers are used to avoid distorting the sideband signal, which might result in the regeneration of the second sideband or distortion of this modulated information signal. So this is what the working principle. So the balanced modulator is used to generate the double sideband suppressed carrier, and this balanced modulator is followed by a sideband filter in order to remove the unwanted sideband. And they already told this initial modulation is take place in the balanced modulator at a low frequency because it is difficult to design the sideband filter at very high frequency. So normally we choose this filter is which is a band pass filter with a sharp cutoff at each side of the filter. Then a carrier oscillator circuit is used in order to place the desired sideband in the filter window. Then the filtered signal is up converted in a mixer to the final transmitter frequency and then amplified before coupling to the antenna. So the linear power amplifiers are used to avoid the distortion of the sideband signal. So this single sideband can be generated or can be formed with the help of a balanced modulator, which is followed by a filter. So the filter means it can filter out the useful sidebands, or based upon our requirement we can either choose the upper sideband or the lower sideband. So the output of this balanced modulator will be a double sideband suppressed carrier, and with the help of the filter we can either filter out the sideband or the lower sideband. So the drawback of this SSB circuit is the sideband filters are extremely very expensive, and the sideband filters did not have the sharp cutoff characteristics. Hence it is not possible to suppress the sideband completely. So this SSB generation circuit consists of a balanced modulator which is followed by a sideband filter. So this sideband filter did not have a sharp cutoff characteristics. Hence it is not possible to suppress the sideband completely. So these are the two drawbacks of this SSB generation. Then advantage of SSB is the telephone system. We can use for the telephone system. So the SSB modulation is suitable for transmission of voice signal. It is not suitable for audio or video signal. This is because in the case of voice signals, a spectral gap exists between the two sidebands. So even though the filter is not having the sharp cutoff frequency, it does not affect the system. So this is the advantage of using SSB signal. So in this slide we are going to discuss the vestigial sideband. So in the last two lectures we discussed different amplitude modulation techniques, that is double sideband full carrier, then double sideband suppressed carrier, single sideband. Now we will discuss vestigial sideband. So before going to that we want to know what is the need for this VSB. So in the video signal, very low frequency modulating component exist along with the rest of the signal. These components give rise to sidebands very close to the carrier frequency, which are difficult to remove by physically realizable filters. Thus, it is not possible to go to the extreme and fully suppress one complete sideband in case of television signals. The low video frequencies contain the most important information of the picture, and any effort to completely suppress the lower sideband would result in phase distortion at these frequencies. So in video signal, a very low frequency modulating signal component exists. So in the SSB generation we used a balanced modulator and filter in order to suppress the carrier, in order to suppress the sidebands. But in case of TV signals, the sidebands were very close to the carrier frequency, and it is not possible to suppress any one of the sideband with the help of the filters. So in that case we have to make use of this vestigial sideband technique. So this distortion will be seen by the eye as smear in the reproduced picture. Therefore, only a part of the lower sideband is suppressed, and the radiated signal then consists of a full upper sideband together with the carrier and the vestige of the partially suppressed lower sideband. So in case of TV signal, both the lower and upper sideband are very close to the carrier signal, and with the help of a filter it is not possible to suppress any one of the sideband. So in that case what we will do is only a part of a lower sideband is suppressed, and the radiated signal then consists of a full upper sideband together with the carrier and the vestige of the partially suppressed lower sideband. So in the 625 line system, the frequencies up to 0.75 megahertz in the lower sideband are fully radiated. So will transmit only 0.75 megahertz of the sideband. The net result is a normal double sideband transmission for the lower video frequencies corresponding to the main body of the picture information. So the figure shows the saving of band space which results from the vestigial sideband transmission. So already told, in TV signal both the upper sideband and lower sideband are very close to the carrier signal component. So if you use the filter method to suppress any one of the sideband, it will be difficult, since it is very close to the carrier signal. So in the vestigial sideband what we are doing is we are transmitting the entire upper sideband, then carrier plus a portion of the lower sideband to the receiver. So because of the filter design difficulties, it is not possible to terminate the bandwidth of a signal abruptly at the edge of the sideband. So practically the sideband doesn't have a sharp cutoff. So what we are doing is we allowed a 0.5 megahertz at either end, so that the attenuation can be avoided. So in case of VSB, we are transmitting a portion of the lower sideband, then carrier, then full upper sideband. So this is what VSB. So in TV signals it is difficult to suppress any one of the sideband. So we are transmitting a portion of the lower sideband along with the upper sideband and the carrier. So this is what vestigial sideband. So vestige means the remaining part. So this is what vestigial sideband. So in this lecture we discussed different amplitude modulation techniques, that is double sideband suppressed carrier and single sideband. So in this single sideband we improved the efficiency. Similarly we are able to reduce the signal bandwidth because in communication we want to make the signal bandwidth as small as possible, then only we are able to transmit more number of signals over a single channel. So by here let's conclude this AM modulated techniques. Thank you.